Welcome on a video on the high frequency models for common base and common collector amplifiers. So in this we will look at the high frequency response of both, at the models and the equations, and they look kind of tricky, but they are not that bad. So let's start with the common base. So common base for high frequency is, as always, we short out the low frequency capacitors. This means that this node over here is grounded. That has some interesting properties for us in the end. DC sources get switched off, becomes grounds. That becomes a ground. And when we replace our transistor with a high frequency model, and for this particular amplifier it won't have a very large effect in any case, is we are going to neglect the effect of the base materials. Okay, that is a very small resistance in general, and from the places that it's seen it will be even smaller, so nobody really cares. Okay, so drawing up a model for this, it will look something like this. And the higher frequency will be 1 over 2 pi r pi c pi plus r mu c mu. So again, we want the impedances seen by each one of these capacitors. Now note, if we make this Rx0, we'll see something immediately, that C pi is grounded, R pi is grounded, and even C mu is grounded. C mu is anchored on this side, so C mu will be grounded together with the outputs over there, and C pi will be grounded with the inputs on this side right here. So Rx get neglected, C pi and R pi is grounded. This is for the base emitter capacitance, or C pi, and we will take C pi sitting here with these two impedances right here. So what is C pi seeing? In parallel with itself, it's seeing RE, it is seeing RS, and backwards through the transistor, or if we were using the T model, we would be seeing small re, or rather r pi over beta plus 1. Okay, so re parallel to rs parallel to small re. And that is all resistance that C pi is seeing. Now, small re is very small for the common base. Rs in general is also a small value. Re will typically be very large, like that. So Rs and small re is responsible for the high frequency cutoff, or specifically for C pi. And they are very low resistance and impedance. So that means our frequency response will be very, very high. That high frequency cutoff. And one of the things that you always hear is that the common base amplifier has a very high frequency response. Okay, so that is number one that's causing it. Number two, looking at our C mu, or the base collector capacitance, is C mu is sitting in parallel with R out, RC, and R load. We see this as a virtual ground point right here. So R mu is just R load prime. So if this is a very large number, your collector and your load is fairly high values, but they are responsible for the higher cutoff frequency with C mu. Note that there is no Miller effect included in here because C mu is not sitting in a strange position. Okay, so the common base has a very high frequency, much higher than the common emitter, and you'll find that this right here is typically because of largeness of RC and R load, the more responsible for the higher cutoff frequency. And that's the common base amplifier. So they're really that easy. Up next, the common collector. So again, we have the same kind of approach. Capacitor, short circuit, ground, ground, and this is going to be off in our later models, but the common base is quite simple. So note that we have Rx, Rs, and Rb. We are going to redefine this again as Rs prime. And other things to note is this node right here is connected to ground. So C mu is connected to ground and will be sitting on this side of amplifier going to ground. Okay, R out will be sitting here next to the emitter and the load going to ground, and that will make our life much easier. So, if we redraw it like this, in perspective of R pi, we redefine this as Rs, we redefine this as R load, and everything will become much simpler if we take the position of C pi. Now C pi is seeing in parallel with itself R pi, but these resistors down here is technically in series with these resistors up here, right? The only difference is these resistors are seen through the amplifier, so they are increased with beta plus 1. So the total series resistance on the outside of this parallel combination right here is Rs prime plus R load prime, but R load prime is larger. So there we have it, Rs prime plus R load prime enlarged, and that whole series combination sitting outside of this transistor is then in parallel with R pi. See it as we make this ground for ourselves and we increase this resistor size and we move it in series with all of this right here. We place it in this position as an extra resistor. So then everything in series goes to ground. R pi goes to ground from this same position right here, and both of them will be in parallel with C pi. Okay, and that is the resistance seen by C pi. We can do the same for C mu. C mu we put in parallel or to ground here from the top of R pi, and on this side we have Rs again, Rs prime. So Rs prime is immediately in parallel with C mu, and then towards this side we see R pi and we see R load prime in series. R load prime is viewed through a transistor, so again beta plus 1 multiplication, and then that series combination is in parallel with this series combination right here. So RS prime in parallel with R pi plus R load beta plus 1. And if you notice, RS prime and R pi just switched positions from the previous equation, like that. So again, no Miller effect, and the common collector also has a very high cutoff frequency, also much higher than the common emitter, but this is mostly for current amplification and voltage following. And there you have it. That is the impedances seen by the capacitors in the common collector amplifier. So in short, if you just know how to move these pieces around on the model, the common collector and the common base has really simple high frequency equations in the end. So yeah, I hope this is helpful. Thank you for watching, and see you again in a next video.